Hello and welcome back. In this video, we're going to solve one of the problems from the back of chapter 6 in your OpenStax book, and that's going to be problem 6-37. So if you get your textbook or look at it online, it'll read, the moon and earth rotate about their common center of mass, which is located 4,700 kilometers from the center of the earth. That is about 1,690 kilometers below the surface of the earth. So the axis of rotation, which I've labeled as point P, is actually in the earth itself. So the moon and the earth rotate about this point. Part A, calculate the magnitude of the moon's acceleration due to gravity at point P. So it's little g at point P. In part B, we want to know the magnitude of the centripetal acceleration of the center of the earth as it rotates about point P once every lunar month. And a lunar month is about 27.3 days. Then we want to compare the acceleration due to the moon at point P and the centripetal acceleration of the earth about point P, and see if those two values are the same, and then reason out if they should be the same or not. So here we are. A, calculate the acceleration due to the moon's gravity at point P. And then in part B, calculate the centripetal acceleration of the earth about point P. And then we're going to compare A and B to one another, the two accelerations that we find in A or B. Okay? So remember that we define the acceleration due to a body as little g, right? So that could be our little g for the moon, right? At point P, right? So that's basically what we're trying to find. And I'm just going to call it A here at this point. So this is the acceleration due to the moon's gravity out here at point P. And remember that the acceleration due to gravity by an entity has a very specific form that involves the universal gravitational constant, big G, the mass of whatever entity you're calculating the acceleration due to. So in that case, it's going to be the moon's mass, divided by the distance away you are from the center of the moon. So in this picture, this distance is going to be labeled as r double prime. That's our r double prime. So let's look at our picture here and notice all of these things that we have defined. Notice that the moon is here and the center of the moon is shown as a dot. The earth is here. The center of the earth is shown as this dot. This point, which is labeled as point P, is the moon-earth axes of rotation. So that's the point about which the earth and the moon rotate. This distance, r double prime, is the distance from the moon to point P. This distance, r prime, is the distance from the earth's center to point P. And then I'm defining big R as the distance between the center of the moon and the center of the earth. Okay, so that's how all those things are labeled. If you do a quick Google search and find the distance between the moon's center and the earth's center in units of meters, you'll find from a Google search that that is 3.84 times 10 to the 8th meters. We are told that the axis of rotation is 4,700 kilometers. When I convert that to meters, that's 4.7 times 10 to the 6 meters from the center of the earth. So I've now defined r prime numerically as well. R double prime, the distance from the moon to point P, is just going to be the difference in the distance between the center of the moon to the center of the earth and the distance r prime from the earth's center to point P. So here is r double prime from the moon center to point P, r minus r prime. So 3.79 times 10 to the 8th meters. So there are those distances. Notice they're off here to the side so I can come grab them when I want. Now let's go ahead and tailor this equation specifically to solve for point A. Okay, so what is this going to go to? So the acceleration is big G. What mass are we talking about? Well, we're talking about the moon's mass. So this is going to be the mass of the moon divided by what distance? The distance is going to be from the moon's center to whatever point I'm interested in calculating the acceleration due to gravity at, and that is at point P. So that is defined here as our r double prime. And I got to square that. So it remains now for me to quickly find what is the mass of the moon from a Google search. And if you do a quick Google search, you'll find that the mass of the moon, and I'll just put it over here, the mass of the moon is going to be equal to 7.35 times 10 to the 22nd kilograms. Okay, so there's the mass of the moon, and now I have all of these quantities. Remember, if I ever forget big G, I just look it up or do a quick Google search on universal gravitational constant, and you'll find it. So let's go ahead and just plug in these numbers. So the acceleration due to the moon's gravity at point P is going to be equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That's our big G. Mass of the moon, 7.35 times 10 to the 22nd kilograms. And then we're going to divide by r double prime squared. R double prime is 3.79 times 10 to the 8th meters. Put parentheses around that whole thing and square it. So now, grabbing your calculator and plugging in these values, you come up with 3.42 times 10 to the minus 5. Okay, and the units, remember we worked them out last time. You could work them out again. Notice the meters squared and the meters squared will go. One of these kilograms, we'll take that kilogram. We'll have a Newton per kilogram left for our units. And a Newton is a kilogram meter per second squared, so the kilograms will also go, and we'll have units for acceleration, which is what we expect. So 3.42 times 10 to the minus 5 meters per second squared. It's a very small acceleration that's due to the fact that we are far away from the center of the moon. Okay, part B now, we want to know what is the centripetal acceleration that the Earth experiences about point P as it rotates about this common point. So the centripetal acceleration, remember, can be written as v squared over r. That's the linear speed that the center of the Earth experiences, divided by the, in this case, that's going to be this distance r prime. But we can also write v as r omega, and we're going to square that, divided by r. And notice that this then was going to give us r omega squared. So if we can find the angular velocity of the Earth, then about point P, then we can square it and multiply it by the distance it is from point P, and then we will have what we were looking for. So let's go ahead and tailor this now using the symbols that we've defined over here to the left side. So the centripetal acceleration of the Earth about point P is going to be how far the center of the Earth is from point P, and the center of the Earth is designated as r prime in this drawing. So instead of r, I'm going to put an r prime there. And then we need to calculate what omega is, okay? So the Earth completes one full rotation, the center of the Earth completes one full rotation about point P every 27.3 days. Okay, one full rotation is 2 pi radians. So omega then is going to be equal to 2 pi radians divided by 27.3 days. We need to get this in proper units. Units are going to be radians per second standard, so that we can go ahead and combine it with our distance and get units of meters per second squared, which is what we're looking for our acceleration here. So 1 day is the same as 24 hours. So notice that the days are going to cancel, and now I have radians per hour, and I want seconds, right? But I know that in 1 hour there are 3,600 seconds. And so now my hours cancels, and now I'm going to have omega in units of radians per second. So going ahead and working out the exact value here, we come up with, give me just a second. We come up with an angular velocity of 2.66 times 10 to the minus 6 radians per second. So that's our angular velocity. And now what we're going to do is go ahead and plug everything in. So our centripetal acceleration is going to be equal to r prime. R prime is the distance from the center of the Earth to point P. R prime is 4.7 times 10 to the 6th meters. And now we're going to divide that by omega, and then we got to square it. So 2.66 times 10 to the minus 6, and that's radians per second. And we're going to square that quantity. And when we plug all of that into our calculator, what do we get? We get 3.34 times 10 to the minus 5. And the units, of course, meters per second squared, because once again, the radians morphs out. That's that strange unit that can morph in and morph out. So look at the two numbers we end up with here, 3.42 and 3.34, both of them times 10 to the minus 5. These numbers are very, very similar to one another, almost exactly the same. And of course, we would expect that. And you ask, well, why would we expect that? Well, because the Earth is experiencing centripetal acceleration. So the center of the Earth is rotating about a circle. Why is it rotating about a circle? Because the force being exerted by the moon's gravity on the Earth is causing it to experience a centripetal acceleration. So the moon's force of gravity is acting as a centripetal force. So remember that when we have a centripetal force acting, if we add up all the centripetal forces acting on an object, it's equal to that object's mass, so this would be the mass of the Earth, times the acceleration of the entity, so the centripetal acceleration. So here's the centripetal acceleration we found for the Earth itself. And notice that this centripetal force is being caused by the gravitational force being exerted by the moon on the Earth. And so this can be described using Newton's universal law of gravitation. So F sub c is equal to big G, product of the masses involved. And that's, of course, going to be the mass of the moon times the mass of the Earth divided by the distance between their centers of mass squared. So this is going to be the mass of the moon, mass of the Earth divided by the distance squared. So we can see that this quantity right here is the acceleration due to the moon's gravity at point P. And so this acceleration, which we calculated from part B, that's part B, and this acceleration from part A should be very similar to one another because the force of gravity is supplying the centripetal acceleration in this particular case. So this is an example of how we can apply some of the things that we've learned to, of course, a real-life scenario as all this stuff describes. So we'll see you next time for maybe more problem solving.